Hi, and welcome back. We're moving into investigation 5 now. And I was looking back at some of my older videos, and I thought maybe I could improve on some of the clarity with writing, making annotations in the presentations, because it is very tough to write clear. Well, maybe that's not a bad example of poor clarity, but you get the point. I think in the past you've seen that sometimes it's difficult to kind of see what I'm writing. It's just maybe I'm writing on this touch screen of my tablet, and it's not, I don't know, it's a little unwieldy at times given limited space. But anyway, we're in investigation 5. We're going to talk about question 1, and we have Jose, who is spinning a ball on the end of a string around in a circular path. And the ball is staying in a plane, so you can think of it as staying in the plane of the screen. Of course, this is the plane is perpendicular to the ground, so it's kind of like a lifeguard sitting on the lifeguard stand twirling the whistle, to give you an analogy. Important. He's going to spin the ball counterclockwise, and we are going to start at the 3 o'clock position. One downside is, these. I thought to improve clarity, I would actually, include the answers in all of the slides, and I thought I'd be able to use the animation feature of PowerPoint and that it would work within this software. Unfortunately, that's not the case. So. It'll be a little anticlimactic in that the answers are going to be there when I toggle through the slides, but we're going to talk about them hopefully in a meaningful way, and as you'll see, even in this slide, we'll always be able to make improvements. And here we go. So in this context, in number 1, we're asked to label quantities on this diagram and describe the position that could be used to describe the position of the ball as it rotates around in this circular path. So total distance the ball has traveled in radius lengths. So here we're talking about distance the ball has traveled, and that would be this arc, right? But we want to be clear here that's to include a reference point from the 3 o'clock position. From 3 o'clock position. In angle swept out by the ball and string in degrees or radians. So we might want to describe the amount of openness subtending this arc that we saw in this first bullet. And by convention we call that theta. But again, we want to be clear here that it's the angle swept out by the ball from the 3 o'clock position, from the, if you want to think of this in terms of the XY plane, the positive x-axis. Here we have the vertical distance from Jose's hand, they meant to say here, to the ball. Hand to the ball. And I actually am not a fan of the wording here, because you might be led to think, oh, his distance from the hand to his hand to the ball, they do this here, and here. And well, you might be led to think that that's the radius, because that's going to be fixed. But nope, they maybe could have improved the wording here by saying vertical distance from Jose's hand to the ball, or we should take maybe from this vertical line described. Horizontal line described by the position of Jose's hand from the ground. This, of course, vertical distance from the horizontal diameter, we know is the sine function. We've defined as a sine function. And then for this last bullet, they say horizontal distance from Jose's hand to the ball. It might have been better if they said horizontal distance from the vertical line on which Jose's arm lies here, right? And then say if the ball were here, then they're describing this distance, right? And going back to here, vertical distance from the horizontal line Jose's hand is on, they would be describing this vertical distance here, right? Okay. Okay, question 2. Define the algebraic form of the function f that defines, function f that relates the ball's vertical distance, that would be d, distance, above Jose's hand in feet. Key here is vertical distance above. That should give us clues to what function we want to utilize, the cosine or the cosine. Hope you all know by now that that's the sine. And that's d is in feet. As a function of the measure of the angle swept out by the ball and string measured in radians as the ball twirls counterclockwise from the 3 o'clock position. Okay, so we should also be specific here that we're measuring theta in radians. Theta is going to be the amount of openness subtending an arc of measured in unit radius lengths. Provided Jose's hand stays fixed, which in this context we're going to assume it does, the maximum height the ball can achieve, of course, is going to be this radius length. So were we just asked to model this in radius lengths, we wouldn't have this 2.3 here. And since our radius is 2.3, we take our function sine of theta, which models circular motion in terms of radius lengths, and then we multiply it by our unit of 2.3 feet. All right, part 3, important question. Suppose that the ball Jose was twirling travels 1 radian per second. How many radians theta does the ball and string sweep out in t seconds? So they're telling us that the ball is traveling 1 theta in radians for 1 second in time. Thinking maybe I should make that clearer. 1 theta in radians corresponds to 1 t in seconds. So I'm using the number 1 on both sides of this equation for clarity, but we don't have to utilize 1 on both sides. To say theta radians is equivalent to 1 t second, or we could just say if there's 1 radian for every t seconds, that we could use these, since there's 1 of each unit, we could just say that theta is equal to t. Okay, so now if we're asked, as we are in part B, to define a function g that relates vertical distance as a function of the number of seconds elapsed, that's time, well then, since our unit is 1 radian per 1 second, or we could think of time in seconds and theta in radians is interchangeable, well then we can define a function that relates vertical distance. That would be the sine of, instead of theta, t. And again, we're modeling distance. And since our radius, since our units are in feet and our radius length is 2.3, we'd have to be careful to multiply the function that drives vertical distance in terms of radius lengths by 2.3. Part C asks us, over what time interval does the ball complete 1 revolution? Well, if a radius length corresponds to 1 second, then we've seen in previous exercises that let's be 2 pi. If when we took a function as in sine of theta and then we change the radius into some unit like kilometers, for example, we noted that doing this did not change the amount of time. That's the whole purpose of this investigation. Did not change the amount of time it took to complete a revolution, but what it changed was this amplitude value. It changed the maximum and the minimum value achievable. So the period, the amount of time corresponding to a complete revolution doesn't change, but the minimum and maximum values do. So as a result, since we're thinking of radians and seconds as being interchangeable, this is going to be no different. We're going to complete one revolution 2 pi seconds. So I'd like to talk about question 4a in a more traditional way. It says that suppose Jose starts applying more rotational force to the ball, i.e. making it spin faster. Instead of 1 radian per 1 second, 2 radians per 1 second. So if we go back to our use of this, thinking that we could think of radians and seconds as being interchangeable if we're going to adapt our units of radians to time, that is openness subtending the arc formed by the ball. Thinking of that in terms of the number of seconds per radian. Well, it tells us that if the ball travels 2 times 1 radian, well then we know that if we're going to multiply the left-hand side of this relation by 2, we have to multiply the right side to keep the scale balanced, if you will, right? So that's where we get this result that theta equals 2t now. Okay, so I'm realizing now that I could probably be a little clearer about this because in one sense, I'm multiplying both sides of this by 2, and then all of a sudden I'm just leaving this factor of 2 on the right side, and that might not be very clear. When we come back, I'll pick it up here and address this issue. I'll see you in the next video.